Here's a tutorial question 29. It starts with the innocent computational part, which says you look at the 3D cube. Here's a quick picture for you. It's a unital cube, they say, meaning that the lengths of the edges are all 1. Now, the first part of the question is relatively simple. It says find the diagonals of the cube. There are plenty of diagonals you can find in this cube, but most of them are just identical. I mean, in length, they are identical to each other. So I just made these red dashed lines to indicate two different ones, which we have to focus on, in fact. One of them is a diagonal over facet of my cube, and the other one is the main diagonal of the cube, like this. This is a very trivial problem if you know what we know already about the vectors. All we have to do, we have to introduce the Cartesian system of coordinates. I just done this for you here. You see this 3 axes, OX, OY, and OZ. You have to give your points coordinates, replace the diagonals with the corresponding vectors, and find the lengths of those vectors via coordinates. That's all there is to the first part of this question. Very simple computational line of thought. The second one is in relation to the 4-dimensional version of it. We will come to it in a second. So I'll just first finish the first part. So I have to give my point some coordinates. Let me just say, if I'm looking at the diagonal AC, I have to supply coordinates to the point A and to the point C, which is a very easy task, isn't it? Given that I already introduced the Cartesian coordinates and given that my cube is unital. The point A will have, point A, coordinates for that point, because it sits on the axis x and my cube is unital, it's 1, 0, and 0. The second point of my diagonal, I'm talking about the diagonal AC, the facet diagonal, it's the point C with coordinates 0, 0, 1. Remember, 1 comes from the fact that the cube is unital. That's it, that's all the input I have to present. Now we can do the very simple computations. First we can find the coordinates of the vector AC. We know how to do that. We have to subtract the coordinates of the origin from the endpoint. Here's the result of that. That's the result of that without doing the arithmetic. Of course I can do the arithmetic. Here it is. And then I have to find the length of this vector, and we know how to do that. That's the Pythagoras theorem. Length of the vector. Remember the notation, 2 vertical bars around the symbol of the vector. And that's where it finishes. Of course, we can compute this. I mean, we can do the arithmetic, obviously. If I do the arithmetic, it will be √2. And that's just basically it. The only difference you have to do, the only difference you have to introduce into this computation when you go after the main diagonal, OD, you have to come up with the coordinates for the point OD, right? What's the OD? What's the coordinates for the point OD? 111, yes, it's the only difference you have to put. So here will be here will be the point O, the origin, which has 000 as its coordinates. Then will be point D here, with the 111 as its coordinates. The rest of the computations will just be identical to what I just presented. And I'll probably stop at that. I'll leave you to figure out the rest of this problem without my help. Any questions? No? Good. Now, we have to discuss what happens if we try to think of a cube in 4 dimensions, in R4. There are two things, there are two sub-questions which we have to address. We have to answer the question, what could be possible lengths for the diagonal of this 4 cube? When I say 4 cube, I mean 4-dimensional cube. And actually, in general, how many vertices this 4 cube may have. So what we're going to do now, we're going to use this world's most powerful graphic chip, because that's the only way we can deal with the 4 dimensions. That's the only way we can deal with the 4 dimensions. So I want to actually approach the part B first. How many vertices this 4 cube, the cube in 4 dimensions, may have. And what I will do, I just try to model my reasoning or model my presentation on 3D cube. Let's just first analyze how many vertices the 3D cube has. Well, it's there's not much to analyze here. We just look at the picture and we say the answer is 8. But rather than just giving you the answer, I'd like to give you the structure of this answer. Because by looking at the structure, how this answer come up with, I mean, it's not like you just need a 1, 2, 3, 4, 5. It's a nice structure, of course, when you use fingers, but I want to show you the different structure. And this different structure will give us the idea how to compute the number of vertices in a 4 cube even without looking at it, but with a bit of the imagination, of course. So let me do it like this. Let me just do it like this. I'll put a bracket. I'll put another bracket like this. Let's just first look at the vertices of square, which is sort of a 2 cube, 2-dimensional cube. It's very easy to list those vertices, right? And how many of those we have? We have 4, right? We have 0, 0. Let me just do like this. I'll just take this bracket. And I'll duplicate it 4 times. So now I have 4 slots to fill in the the coordinates for the square, right? So first one is obviously 0, 0. Next one will be 1, 0. Next one will be 1, 0. Next one, well, let's go 0, 1. And the last one, I'll go 1 and 1. I don't have much of a choice actually for the last one. Now, look what we do when we take these 4 of a square and we just try to extend them to 3D cube. What we do, we just introduce the third coordinate, which I'm not going to put like in numbers, but which I put like a little circle here for the third coordinates, right? We need the third one here, we need the third one here, we need the third one in here, and obviously we need the third one in here. Now, let's just try to see how we fill this third one in a structured way. If I fill all of these third ones with zeros, what I will come up with? I will come up with this bottom facet, right, of my 3D cube. If I fill all of these empty spaces, all of these circles with zeros, it will be my bottom facet of a cube. And if I fill them with ones, I will come up with this top facet. This one, and this one. So here's the structure I was trying to hint to you. The 3D cube, or the vertices of the 3D cube, they split in 2 groups. One square and the other square. One with the z component 0, and the other with the z component 1. Well, we can do now the same trick with the 4. Now we can try to do the same strategy with the 4 cube, right? We can take all of the vertices of the 3D cube, right? All of them here. I'm not going to now write all of them, all of these 8. But now, if I just introduce the 4th one, let me just zoom in a little bit here. If I introduce the 4th one here, and remember, now I have another 4 down here, right? Is my dots representing another 4, which I'm not going to write this, but we use the imagination to think of them. So if I now enter this 4th place in all of my 8 coordinates, again I have 2 possibilities. I can fill these 4th places with zeros, and that will deliver one facet of the 4D cube, which will be the 3D cube now. And if I fill them with ones, it will be another facet of 4D cube, which by itself is a 3D cube. Are you with me on this one? I hope you are. But the numerical answer now, I think you can tell me now the numerical answer, what will be, how many vertices my 4D cube will have? 16. 8 for the one facet, and the 8 for the other facet. And we now have a clear understanding of the structure of all of these vertices. If I now summarize what I just said, what I just presented as a structure to you, I can say that if I just give this formal look for the vertex of the 4D cube, let me call it A. If I call the components of this, or coordinates of this, in x1, x2, x3, and x4, I can now, with confidence, say to you that each of these numbers, each of these numbers, xk, it's either 0 or 1. And any combination of 0 and 1s is possible. And altogether we have 16 of such combinations. And that finishes my answering of part B in relation to the four-dimensional cube. Now, the part A now is relatively easy because now I can say like this. If I now, let me take now another symbol. Let me call it B, y1, y2, y3, y4, like this. Again, each individual's y's, either 0 or 1. So imagine now I have two vertices of my 4D cube. That's one. This is the other. Finding the diagonal of this 4D cube will be just following this method. We just have to keep using my imagination just to keep ourselves on the right track. So what I have to do, I have to find the vector AB, right? Let's just see. Oh, easy. Coordinates for the vector AB. Here they are. Let me just lift it. Here's my coordinates for the vector AB. Remember, A and B, some arbitrarily chosen vertices of my 4D cube. All of them have this structure. We just discovered this with you. And now for this vector, all I have to do, I have to find the length of this vector. Again, I will write the formal expression. You don't have to copy it. It's rather lengthy expression now because there will be 4 terms involved in there. I will publish in the notes of this one anyway. I mean, these screenshots, if you've been following my website, you know that these screenshots basically go on the website anyway. But if I find this length, it will take time before it will open up. It will be a long expression, but you shouldn't be intimidated by this expression because we perfectly know what the components in that expression. Here we go. We perfectly know what will happen with these individual terms, right? Because each y and each x is either 0 and 1. Yeah, either 0 or 1. When you take a difference of such two numbers, the result will be, how many options for the result will be? 1, 0, and minus 1. Of course, square will kill one of these options. Square will make -1 just 1. So basically, it's a long expression, but this bracket, after you square it, will have only two values, 0 or 1. This will be either 0 or 1. This will be either 0 or 1. I don't have to type it again. I can duplicate it. And this will be either 0 or 1. And so when you go after the length of this diagonal, you can now play with all combinations. Either you have 1 bracket 1, the rest is 0. Either you have 2 brackets 1, the rest is 0. Either you have 3 brackets 1, the rest is 0. Or the final is when you have all 4 brackets 1s and none of them is 0. And that will give you possible values for the lengths of diagonals, which is a loose term right now, because when you have only 1 bracket 1, obviously it's not a diagonal, just the edge, right? Because if only 1 bracket is 1 and the rest are zeros, it means that your points are different and only in one position, which is a clear sign of the edge of my 4 cube rather than the diagonal. It's again, I resort to my imagination and my experience with the 3D cube, and I just extrapolate this to the 4D cube. So to summarize now, I can say that the possible values for the length of the diagonals, if I exclude the case of the edge, so I will start with the case where we have 2 brackets 1 and the rest is 0. So the possibilities for the lengths of the diagonals will be either square root of 2 or square root of 3, and the final one will be square root of 4, which is just 2. These are the possible lengths of the diagonals for the 4D cube.